Well, it's a lovely frosty morning, so as you can see I've come outside for a bit of fresh air, which makes a change from being stuck indoors all the time. We've had so much rain recently. This is the first real day of winter, I think, that we've had for a while. And it's lovely to see crisp blue sky, crisp, fresh frost on the ground. It's just gorgeous. But yeah, it really got me thinking about frost and the process by which frost forms. Of course, the way tiny sort of water particles and things in the air stick to things, and then they grow into these sort of hair-like kind of fractal-like structures, which is kind of interesting actually. And it got me thinking, how would we go about simulating that in a computer? And I thought that would be a really interesting thing to do. So I think that's what we should look at. We should have a look at writing a simulation of frost, and then we could admire the beauty of frost without having to come outside where it's cold. I appreciate the fresh air, but I've been out filming now for a while. My hands are quite numb. I really think it's time we go back inside, and yeah, let's see what we can do in the computer instead, and warm up maybe with a nice mug of something hot. Okay, let's see what we can do. Whew, okay, right, there, well, back inside, back in the warm, that's good, and I do indeed now have a mug of something hot, which is very welcome, I have to say. I see, making my glasses steam up. Oh, it's always a nice feeling when you've been out in the cold. Okay, I think we should switch to the other camera. It's really nice to be back in the warm after being out there in the cold. Always good to get fresh air, especially on a crisp, fresh, frosty morning. But yeah, it was a little bit on the chilly side, so nice to be back and toasty and warm again. So as we've just been seeing, what we're going to talk about today is frost, and we're going to talk about particularly how we can write a simulation of the process by which frost is formed. Now, frost actually forms when water vapour in the air comes into contact with a surface at a lower temperature than the surrounding air, and this causes actually a desublimation process. So the water vapour in the air immediately passes from its gaseous phase to a solid phase, and this forms the crystals of ice that go on to grow and become frost. And that creates the kind of classic frosty, almost sort of hair-like structures that we're used to seeing. So the question becomes one of, well, how could we actually go about simulating that? And this would allow us to enjoy the beauty of frost without having to go outside into the cold. If, I don't know, I'm just kidding, no substitute for a bit of fresh air, obviously, but it's an interesting question nevertheless. How would we go about creating a computer simulation of that process? And it turns out it's really not that difficult. What we need to do first is to create a simulation of Brownian motion. So we're going to work on, and we're going to make an assumption, and we're going to assume that we can model the water vapour as being a series of very small but discrete particles. This is not necessarily entirely realistic, but it's a simplification that allows us to really quite easily create a simulation of this process. So what we need to do first is think about Brownian motion. Now, Brownian motion, of course, is the motion of a particle in a liquid when it gets repeatedly knocked about by the motion of the particles of that liquid, or in this case the air, the gas, right? So the first thing that we need to do is write some code to simulate that, and actually it turns out that we can do that quite simply using an algorithm known as a random walk. Okay, so that's what we're going to do now. We're going to jump to the computer and we're going to look at creating the code to implement a random walk. So here we are. I'm in my text editor. You, of course, can use any text editor that you want. And this is my Python code that I've created. Now, I've already gone and fleshed this out with the basic structure of what we need for a Pygame application. So we import random because we're going to need random numbers. We import numpy and we import Pygame. And then we define the class for our application, and we have our methods, the initialization method, which simply sets the size that we want to 640 by 480 pixels. We then have the onInit method, and this calls pygame.init and then pygame_display.setCaption to give our window a title. And then we generate our display surface. Now, we talked a little bit about display surfaces in the previous video on the Lorenz attractor. There'll be a link in the top right of the window. And then we simply call the pygame_display.setMode method and pass that the size of our window, and then that generates our display surface. And we create a flag called isRunning, and we set that to true. Now we have the onEvent method, so this is just for handling any events, and just as the same with the code we did for the Lorenz attractor, the only event that we're interested in at the moment is pygame.quit, If we get that event, then we set our isRunning flag to false. Then we have the standard layout of a Pygame application. We have the onLoop method, which currently does nothing, so we set it to pass, and the onRender method also currently does nothing, so we set that to pass. And then onExecute, so this is the method that's called when we first start the application. We call the onInit method, and if that returns false, we set isRunning to false to make sure that the application will stop. And then we begin a while loop. So while self.isRunning is true, we continue with everything in this loop, and then we loop through every event in pygame.event.get, and we call the onEvent method that we've defined with each event in that object. And then we simply call the onLoop and the onRender methods, and we continue looping like that until isRunning is set to false, at which point we drop out of that while loop, and then we execute pygame.quit, and that causes the application to finish. And then we just have this down here to actually cause everything to work. If we run this Python code just as it is, then we create an instance of the application called T, and then we call the onExecute method in T. So if we go ahead and run that code, and bring that over here, so as we can see, that creates exactly what we expect, simply a blank window with the caption or the title random walk, exactly what we want, and it is 640 pixels wide by 480 pixels high. So that's the basic structure of what we want, but really no more. We have to do a little bit more work to actually get our random walk. So let's close that for now. Now, how do we actually go about making a random walk? So I've already commented this already, that this is a basic implementation of a random walk. It's essentially modeling Brownian motion. This is, of course, a simple first step towards modeling the formation of frost. Now, we're going to need to define some extra things. We need, first of all, to define starting points for our random walk, which we're simply going to do like that. So we simply set the starting point to be the width of the window divided by 2 and the height of the window divided by 2, so that's simply in the center of the window. We will also need to define variables to store our current x and y coordinates, so we can store the position of where we are in the random walk. And we are using a display surface, so we should, of course, initialize that first. And we're going to use the pixel array method with Pygame so that we can access individual pixels quite quickly and quite easily. Because we want this to be a pixel by pixel process, we're going to use the pixel array method, so we're going to create a variable to store our pixel array, and finally we're going to use a variable to store our pixel color. Okay, so now what we do, just here in our onInit method, after we create the display surface, we need to create our pixel array, and that's very simple. We do that simply like so. So we just insert that line, that pixel array is a pygame.pixelArray, and we just pass to it the display surface object that we've just created. And finally, we are going to define the color of our pixel, which we're going to define as being full red, 25500, which gives full red. Okay, and that's still not going to do anything, of course. All we've done there is set everything up. So now we need to look, what do we do in onLoop? So what do we do? In each loop, so every time we call the onLoop method, we want to add 1 pixel to our random walk. So the first thing that we need to do is to choose a random direction in which to move from our start point. Now, this is actually quite easy, and we can do this using the random.choice function. So just like that. So what this will do, we create a list of these. So we have possible movements in x and y. So the first possible movement is no movement in x and a movement of positive 1 in y. The second possibility is no movement in x and a movement of negative 1 in y. Third possible movement is a movement of positive 1 in x but no movement in y. And finally, we have a movement of negative 1 in x and no movement in y. So the random.choice method simply will pick one of these 4 possibilities and will return this into new dir. Okay, so then we are simply going to extract our delta x and delta y from that, which is very simple, dx comma dy equals new dir. And then, of course, we simply need to apply these to the x and y coordinates. So we have self.x plus equals dx and self.y plus equals dy. So that is simply doing adding dx to x, and that's adding dy to y. So if dy is positive, we add 1 to y. If it's negative, we take 1 away. Okay, now since we're making modifications to the coordinates and everything, we need to make sure that we check that everything still fits within the screen. Okay, so this is really very simple. We just have if self.x is less than 0, then we set self.x equal to 0. If self.x is greater than self.width minus 1, so if it goes beyond the edge of the screen, then we set self.x equals self.width minus 1, and we just do the same for y. If self.y is less than 0, then self.y equals 0. If self.y greater than self.height minus 1, I prefer spaces around those. There we go, like that. Then self.y equals self.height minus 1. So that will ensure that no matter what changes we make to our point, it's still going to fit within the screen. And that is actually everything that we need. So that modifies, so every time we come through loop, that is going to modify our x and y coordinates. And yes, so all we need to do now is then make sure we have some code that actually renders that. So every time we call on render, we are simply going to update the pixel array, and we do that very simply with self.pixel array square brackets self.x self.y, like so, equals self.pixel color, just like that. And then of course we need to update the display, otherwise nothing will happen. Update the display, which we call pygame.display.update, just like that. Okay. So that is everything that we need to implement a very basic random walk. So if we go ahead and run that code now, let's see what happens. I'll bring that over, and you can see that, let's have a look, yes, and you can see that as that runs, that is obviously walking around, so it's every time it goes through on loop, it is choosing a random direction between those 4 possibilities, which are up or down in y, left or right in x, and then it's modifying the x and y coordinates, and we're simply then rendering that every time. So we see that we get a very simple random walk. This is actually the basis of what we're going to use to really do our simulation. So what we're going to do is implement lots and lots and lots of these random walks, one after the other, and we're going to detect when the particle in the random walk collides with the existing frost crystal, we're going to call it, and then at that point we're going to make it fixed to that. So the first thing we need to be able to do that is to be able to detect when we're hitting another pixel that's already been fixed. So let's have a look at how we would make that work. So if we just close that for now, and let's go back to our code. So we want to detect when we hit another pixel. So I'm going to look in my on-loop method, and what we're going to do, just to check that we can do this properly, we are going to check if this pixel has already been set. Okay, so when you notice that a lot of, while the random walk is running, there's nothing to prevent it going back over itself. So we can check that. So if we do if self.pixel array at the new location self.x self.y, if that is equal to, now we're going to define this as a hexadecimal, FF0000, that is full red. So FF is 255, 000, and 00 is obviously 0. So that detects full red. So if the pixel is red, then we're going to modify our pixel color to yellow, like that. Okay. Obviously we need an else self.pixel color equals red. Okay, so what that will do now, every time through the loop, it's going to check if the new pixel that we're moving to has been set already. If it has, we set pixel color to yellow. Otherwise, we leave pixel color as red. And of course, in the onRender method, we draw each pixel using the pixel color method. So now if we run that code now, there we go. So now we see that the random walk runs as before, except now when it goes back over itself, it will set the pixels to yellow. So we can see that this is an acceptable way to detect whether a pixel has been set or not already. So that's the basic process that we're going to use. We're going to define the new position that we're going to move to, and then we're going to check if that position has already been allocated as part of the frost crystal, and if it has, then we're going to fix our pixel in that location, and then we're going to repeat that process. Okay, so we can close that now. Okay, so let's have a look at how we would actually do that in practice. So what we want to do now is see how would we actually go about creating a very simple simulation of frost. So this is everything that we need to do the random walk. We're going to have to make some minor changes to this now. The first thing we're going to do is in the init method of our class, we're going to define a new thing called a new variable, which we're going to call update flag, which is initially defined as false. Okay. Just that. We don't need to change anything in onInit, and we don't need to change our onEvent method at all. Now we're going to do something a little bit differently in onLoop. So just as before, we leave this as it is to choose the new direction and extract dx and dy exactly as we did before. But now what we're going to do is we're going to define new x is equal to self.x plus dx, and here new y is equal to self.x plus dy. Okay, so instead of simply modifying the x and y coordinates immediately, what we're going to do now is create a new variable called new x, which is equal to the previous x value plus dx, and new y, which is equal to the previous y value plus dy. So instead of checking, there's no point now checking self.x and things. What we need to do now is modify new x. So we check that if new x is greater than 0. If it is, we set it. If it's less than 0, we set it to 0. And we're simply going to replace all of these here. So that also becomes new x. Okay, and obviously here that becomes new y. And here that becomes new y. And that becomes new y. And that becomes new y. Okay, so that's pretty basic. Now, you're probably wondering why do we have to change to doing it that way? And the reason is because what we want to do, we want to check if the position that we're about to move to has already been allocated as being part of the growing crystal, the frost crystal, or not. If it has, then we want to set the pixel that we're currently at as being part of the crystal. So we need to keep a record of the position that we are at now, separately from the position that we're going to move to, if that makes sense. Hopefully, if you look over the code, I think that will make sense. Now, we've already implemented our code to check if the pixel that we're going to move, that we are moving to, has been set. The only thing we need to do here is modify this to be new x and new y. So we check if the pixel we're going to move to has already been set to red. Now, if it has, instead of changing the pixel color, we are going to modify that. So we set update flag equals true, else self dot update flag equals false. Okay, just that. And also, in the case that if the pixel hasn't been set, we want to modify our x and y coordinates so that the next time we come back through this loop, we start from the new position. So we have self.x and the self.y equals new x, new y, just like that. Okay, so in the event that the new pixel hasn't already been allocated to the crystal, which means it hasn't been set to red, then we modify x and y to be our new x and new y, and then the next time we come through this loop, we will start this whole process again. If the pixel that we do want to move to has already been set to red, meaning it's part of the growing frost crystal, then we simply set update flag to true, and we don't do anything else. Now, we need to make changes to our onRender method. So at the moment, onRender does stuff every time that it's called, every time we come through it. Now, we don't actually need to do that. We're not interested in drawing the particle as it goes about its random walk. Doing so would make our simulation run unacceptably slowly. We're only interested in actually drawing something and updating the display when the crystal actually grows, when something really changes. So what we're going to do is on render, we're going to add if self.update flag. So if update flag was set to true, then we're going to do stuff. Okay, so we need to tab those in. So what we do, and let's just be extra clear about that, so we can just replace that as the hex code. Okay, just so that it's definitely the same as that, but I mean, of course it is. So if the update flag has been set, the first thing that we do is set the pixel that we're currently at to red. And then oops, I don't need that. Then we're going to update the display, which we do as before. And then finally, we need to reset the update flag and the random walk. Okay, because if we get to here, we don't want this to happen again. So we set update flag back to false. Oops, yeah, of course need a capital F in Python. And now we reset X and Y back to the start coordinates. Okay, and we reset X and Y back to the start coordinates so that the random walk will begin again. So every time every time a pixel is allocated to the growing crystal, then we reset the update flag and we reset X and Y back to the start point to start a new random walk. There is one thing that I forgot to do. Of course, init. Yeah, here we go. Init, we actually need to set a seed point. So we didn't set any initial points, okay? So the problem is, of course, that will just run and run and run because there are no pixels allocated as seed points. So we're going to modify the pixel array, self.pixelArray, and we're going to put this at self.startX and self.startY. Now there's no point putting it exactly at the same place as our starting position, so we just do start y plus 10, and we set that to 0xff, so create a red seed point, and so that we can see it, we call pygame.display.update, just like that. Save. Right. Now if we run that code now, yes, so now we have a red pixel at the center of the screen, and if we wait patiently, we should see that that will grow eventually. Now, of course, what's happening now is that in the background, the simulation is running, and the random walk is going about its business. But of course, because it can go around the whole window, we have no idea of knowing where it is, and there's actually a very small chance of it colliding with the point in the center. And as we can see, we can wait for quite a long time, and nothing really appears to be happening. And there we go. Finally, we see that change just a little bit. So eventually the random walk collided with our seed point, and we got a result. The crystal started to grow. Now, obviously, if we leave things like this, it's going to be tremendously slow. It's going to take a very, very long time to really get anywhere. And the reason that it's so slow is because the random walks are happening across the whole of the window area. So it can take really a long time for a particle to collide with the seed point or with the growing crystal. To make it faster, we're going to create or define essentially a domain around the growing crystal. Okay, so we know where the crystal is, and we know its extents. We can keep track of the size of the crystal as it grows, and we know there's not really any point simulating the motion of a particle far away from that. So we're going to define a region which we're going to call the simulation domain that exists around the growing crystal, and as you will see, that will lead to a significant improvement in the speed of our simulation. Let's have a look at that now. Okay, so back in my text editor, we have actually some fairly big changes to make now. So the first thing that we should do, oh yes, see now I forgot that on the last one, frost with simulation domain. Okay, so we'll change the title of our window. Now, as I mentioned before, what we're going to do differently to what we did before is we're actually going to define a domain over which our simulation will run. So to begin with, we need in our onInit method to set up some variables. So we need min_x and min_y, and we need max_x and max_y. So those will be used to store the limits, the size of the actual current growing crystal. But what we're actually going to do is our domain is going to be larger than that. So we're going to set a pad size, so of 20 pixels. So what we're going to do is we min_x and min_y, max_x and max_y define the extent of the growing crystal. And then we define our simulation domain as being pad size pixels larger than that. Hopefully that will become obvious later. So we need to set up, we can see actually how that works when we define these. So we're going to set up variables for our domain. So we have domain min_x and domain max_x and domain min_y and domain max_y. Okay, update flag that we keep, and we're going to modify. What we're going to do, we're going to change this to leave that. And one last thing that I want to add, self.crystal color. So this will be the color of our growing crystal, and we're going to use a slightly different value of 80, 80, 80, which is mid-gray, and just makes a slightly more sort of icy look to everything, I found, which is better. So we're not going to use pixel color anymore, so let's just get rid of that. In fact, we can also delete it from here. Pixel color we don't need for anything, so let's get rid of that. Okay, and we set our seed point. We do this exactly as before, except now we call this self.crystal color, like that. And we don't need to change anything else there. That's all fine. So now, an on-loop method is where things are going to be a little bit different. At the moment, this defines not only the directions that we move in, but it also actually defines the connectivity that we're testing. So we choose a new direction based on one of these four choices, but that is either up, down, left, or right, or north, south, east, or west. Okay, so but it doesn't have any accounting for the possibility of moving northeast or southwest or northwest or southeast. So we're going to extend the number of possible choices here to account for that, which we can do as follows. And then just check that we have the right number of parentheses. Okay, so now that gives us 8 possible directions that we can move in, which also defines our connectivity. This code we're going to leave the same, new x and new y. Okay, but now what we're going to do instead, we want to define our point to make sure that our point stays within our domain. So instead of self new x less than 0, new x less than domain min x. Okay, and if new x goes less than 0, instead of simply stopping at the boundary, we're going to make it wrap around to the other side. So we want it to go to domain max x. So you see what happens there. If new x is less than domain min x, which means our point has moved off to the left, then we modify new x to be equal to domain max x, which means it comes back onto the right. So we're implementing a wraparound, and we're going to do that for each of these variables. So if new x is greater than self.domain max x, then we set new x is equal to domain min x. And if new y is less than self.domain min y, then we set new y equal to domain max y. And if new y is greater than self.domain max y, then we set new y to domain min y, just like that. Okay. Now we have a little bit more work to do here, where we check that if this has already been set. The first thing we need to do is set that to self.crystal color. Okay, and obviously the first thing we do is set update flag, just as we did before. But what we need to do now is modify the extent of the simulation domain if necessary. So as the crystal grows, we want the domain to expand with it. Okay, so we need to measure the size of our crystal. So we very simply do if self.x is less than self.min x, then self.min x equals self.x, and we have if self.x greater than self.max x, self.max x equals x. So you see all we're doing is modifying min x and max x to be equal to the maximum extent of our crystal. So if self.y is less than self.min-y, then self.min-y equals y, self.y, and I see I got that wrong here, it needs to be self.y. And if self.y greater than self.max-y, then self.max-y equals self.y, okay? And then, based on that information, we need to modify the actual domain itself, okay? So we simply do this as follows, okay? So that's the first line. So self.domain min x is equal to the maximum of self.min x minus the pad size, or 1. That is a shortcut way of making sure that domain min x can never be less than 1. If the result of this sum becomes less than 1, then the maximum function ensures that we stick with 1. And then we're simply going to do the same thing for others. So domain max x is now equal to the minimum of self.max x plus self.pad size and self.width minus 1. So if this sum here becomes greater than self.width minus 1, then the minimum function ensures that the answer will always be self.width minus 1. Okay? And then we very simply just do the same thing for min y and max y. Okay? Just like that. So that modifies the domain. So we modify min x and max x, min y and max y if necessary, and then we use those values then to make sure that we define the extent of our domain. And then everything else there is the same. Now on render, we need to make some changes. So first of all, this has to be self.crystal color. Okay. And then display update as before. Set update flag to false. Now, this is a problem. So here, what we did every time that we reset the random walk, we simply reset it back to the start point. And that's actually really not very realistic. And what we need to be able to do is to define a random start point around the edge of our domain. Okay, so let's have a look how we would do that. What we're going to do is just simply get rid of that code. Okay, and we are going to select one of the 4 sides of the domain to start from. Okay, and we can do that very simply. So we've got 4 sides. So we simply say new side equals random.choice 1, 2, 3, or 4. So that's going to pick one of those numbers, 1, 2, 3, or 4. Right, and then we simply say if new side is equal to 1, if new side is equal to 1, then self.x equals self.domain min x. So in that case, we fix the x value along the left-hand edge of the domain, and then we're going to choose the y value to be a random position somewhere along that side, which we do simply like that. And then we carry on much the same way, else if new side equals 2. Okay, in this case, now we're going to pick the x value to be a random value along that edge, and we fix the y value to being self.domain min y. Okay, and elif new side equals 3. Okay, so in this case now we're going to fix x as being self.domain max x. I think you can probably see the pattern here now, and we define y like so. Okay, random position within that edge, and then our final condition, else. In this case now we set x to somewhere along the 4th edge, like so, and we fix y to be self.domain min x. Y, sorry, domain.min y. Okay. So we see that we've, oh, interesting. Of course, max y, there we go. And let's just check. I think that is everything that we really need to change. We don't need to change anything in here. And so what we've done, let's just recap briefly. So we defined variables to store the size of our crystal. There's a min x, min y, max x, and max y. So they define the limits of the crystal as it grows. And we then define a domain that is pad size pixels larger than the rectangle surrounding the crystal. Now in onLoop, we now define our 8 neighbor connectivity and movement possibilities, and we simply make sure, instead of checking just with the screen, we check that our new x and new y are within the simulation domain. If they go beyond the bounds of the simulation domain, we actually wrap them around to the other side. Okay, and then we also modify the extent of it. So every time we come through, when we add a pixel to the crystal, we then modify the extent of the simulation domain by modifying min x, min y, and max y accordingly. And then we modify the domain, taking care to ensure that the domain can never expand beyond the size of the window. And then on render, we've just added some extra choice now, so that when we pick a new start point for our new seed point, we pick a start point that is along one of the 4 boundaries of the rectangle that defines the simulation domain. And that is everything that we need to do. If we run that code now, there we go. We see that now, so because we've defined a domain around our crystal, we see that we get much faster growth now. And if we let that run, we can actually watch as the crystal begins to form. Now it will appear to get progressively slower as the simulation domain expands. The reason, of course, that this runs so much faster is because we're limiting the extent of the random walks. So with the version that we had before, the random walk was free to move around across the whole of the window. Now that might be more physically realistic in some ways, but it meant that the simulation ran incredibly slowly because the probability of that random walk striking the seed point, or indeed the growing crystal, was really small. So what we've done now is to define a simulation domain around our growing crystal, and that means the random walk is confined to that domain. So it's much more likely, so the probability of a collision occurring is of course so much higher. And we've also modified it now so that at the edges of the domain, the random walk will simply wrap around to the other side. That also helps with making it faster, but is actually also, if you think about it, a little bit more realistic what might happen. So as we can see, that starts to give really very pleasing results already. And yeah, it's really a very simple thing. So one of the things that we can do now, if we stop that, one extra thing that's just a little bit interesting to do is we can play around with the relative probabilities of how our particles are moving. So if you imagine, if it was a slightly windy day, you can imagine that the frost, indeed you may have seen this out in nature, that the frost will tend to grow in at a particular angle depending on the wind. So what we can do is influence the relative probabilities of our particles moving in certain directions. So the probability at the moment is completely even for each of the 8 directions. But for example, suppose we wanted to double the relative probability of it moving in the positive x direction. What we need to do is add an extra option here. So now we have 2 here that represent a possibility of moving in the positive x direction. So that means the relative probability of a movement in the positive x direction occurring is now twice the probability of movements in any other directions. So if we run that now, bring that over here. So we should now see something slightly different. Yes, so you see what happens. The simulation now favors growth in the negative x direction because we are encouraging our particles. They're more likely to be moving from left to right. And because they're more likely to be moving from left to right, they're more likely to collide with the left-hand side of the growing crystal. If you think about the edges of the domain, and this only works because we implemented the wrapping around. Okay, so they move in this direction. If they go up beyond this limit of the simulation domain, they wrap around to the other side. So now we see we get much more rapid growth in one particular dimension. And that's actually quite an interesting thing to play around with. I would encourage you to have a play with the code and try changing some of the relative probabilities of different directions and see what kind of effect you get. The other interesting thing to do with this would be to define a more complicated shape to act as the initial seed point, making sure that your original starting point and the domain to start with are in positions to accommodate that. But this is really, it's a very simple algorithm, and yet it yields a surprisingly realistic looking simulation of the occurrence of frost. So we've made many approximations and assumptions really in creating this simulation. It is very simplified compared to what happens in the natural world. But even so, it actually, as we can see, at least visually, generates very pleasing results that really do appear to simulate the physical reality of the formation of frost. And it has the advantage that we can now start to enjoy the beautiful patterns that frost can make without having to go outside and get cold. I'm just joking. I really like the fresh air, and crisp frosty mornings like this morning are just great. Anyway, listen, that's everything that I want to talk about in this video for today. If you've liked this video, please hit that like button, and please do remember to subscribe to my channel so that you don't have to miss any future videos. Anyway, that's enough from me for today. I really look forward to seeing you in the next video. Bye!